Hey folks, welcome to this episode on the rate law. So we know that concentration has an effect on the rate of the reaction. Now, to see what effect it actually has, we do a few experiments. We know that increasing the concentration of a set of reactants will increase the number of collisions and therefore increase the probability of a successful or effective collision. But we want to see what actual effect it has. Now, we do this experimentally. Here we have a reaction where A reacts with B to create C and D. To see what effect changing the concentration of one of these reactants has on the overall rate of the reaction, what we have to do is we have to keep one constant and then change the other one in a number of trials. So what we're going to do is we're going to keep the concentration of B constant and change the concentration of A. And we're going to see what effect changing that concentration will have on the overall rate of the reaction. So you can see here that we have our initial concentrations plotted for A. We have 0.025, 0.05, 0.1, 0.15, and 0.2. Our reaction progresses in this black line over here. But what we want to try to see is we want to see what the initial rate of the reaction is. And so we draw a tangent to our initial line over there. Why do we do this? We know that this rate is going to be the fastest rate, and it's actually the only time that we really know what the actual concentrations of our reactants are. So we draw our instantaneous rate and we figure out what the rise of the run is of that. Now you can see graphically that as we increase the initial concentration of A, the rate also increases. So if we double the initial concentration, we also double the rate. And that's shown by this linear relationship here. So if we take this data and we plot it onto the graph, we can see that as we go from 0.025 to 0.05, we're seeing an increase, a doubling of the actual rate. Now this line here is our slope of the line, and mathematically with y is equal to mx plus b, our slope would be our m. In this case, the slope in chemistry, we use a variable called k. So this k is consistent with this particular reaction, meaning that if we know what our concentration is and we know what K is, our constant for the reaction, we will be able to know what the actual rate is going to be. And so therefore the rate is actually proportional to our constant and our initial concentrations. However, we don't know how this initial concentration, for example doubling it, will actually have on the rate of the reaction. Now we do this experimentally, but we can then use some mathematics to express this. And we express this using something called the order of reaction. Now this order of reaction is actually just an exponent that we use outside of the concentration of that reactant to show what effect it has on the overall rate. Now when we doubled our A, we could have had three scenarios. If we doubled A, the concentration of A that is, we could have doubled the rate, we could have quadrupled the rate, or it could have had no effect at all. And what we saw based on the graphs, we saw that as we doubled this, we also saw a doubling in the rate. And so mathematically, we're going to express that using a specific exponent. Now that's an example of something called a first order reaction, where we double the reactant and that doubles our rate. If we tripled the reactant, that would triple the rate. If we quadrupled the reactant, we quadruple the rate. So whatever we do to the concentration of that particular reactant will have an equal magnitude change in the rate of the reaction. And mathematically, that's expressed using the exponent 1. So if this was 2.0, our initial concentration, then our rate would also be 2.0. We also have a second order reaction where if we change the concentration of a reactant, it has an exponential increase in the rate. Here we have a new equation, and what we're going to do is we want to see what effects changing the ClO2 has on the overall rate of the reaction. So in this case, what we're going to do is we're going to keep our OH consistent or constant, and we're going to gradually increase the concentration here, measuring the rate of the initial reaction. And what was seen was, again, this exponential relationship. As we doubled the concentration of ClO2, the rate of the reaction was quadrupled. So mathematically, this is expressed using an exponent of 2, meaning that if this concentration was 2.0, our rate would be 4.0. However, what's interesting is that in the same reaction, the reactants have different effects on the overall rate of the reaction. We saw that doubling this species quadrupled the rate of the reaction. But what about this one? What effect does this one have on the overall rate? So what we're going to do is we're going to keep this constant, the ClO2, and we're going to gradually change the concentration of OH minus and see what it does to the overall rate. Now, doing that, we get a straight line, meaning that no matter what we do to the concentration, the initial concentration of OH minus, we won't have any change in the rate. Doubling it, we'll have no change. Tripling it, no change. Quadrupling it, no change. Mathematically, this is expressed using a exponent of 0, meaning that no matter what we do to our concentration of this reactant, in this case our A represents our OH, the rate will not actually change. So to put all these things together, we build an expression that expresses what's actually happening in our reaction. And we call this our rate law. Now, sometimes this is called the rate equation or the rate expression, but it all basically means the same thing. It shows the rate of the reaction, and it's proportional to the product, the multiplication, of the initial concentrations of the reactants to raise to some kind of power. Now, the power does not have to be equal to the stoichiometric coefficients of the balanced equation. So here we have X, which is one of our reactants, and Y, which is another reactants, and their coefficients are A and B. Now you can see that the power that they're raised to are not in fact the small a and the small b. Sometimes they might be equal to A and B, but other times they might not. These exponents, when we're talking about rates of reactions, they have to be done using labs. They have to be determined experimentally. So again, those exponents, aka called the orders of reactions, they can have any real number value. They could be zeros, they could be fractions, but the one thing that they don't necessarily have to be is equal to the coefficients of the balanced equations. Again, sometimes they might be, sometimes they may not. The only way to determine what they are is to look at experimentally. Now, what does that mean experimentally? It means keeping, if we had two reactants, like our A plus 2B gives us our products, what that means is keeping one of them constant while changing the concentration of the other and seeing what effect it has on the rate. And then keeping this one constant, changing the 2B, and again, seeing what effect it has on the rate. So we have to do that in a number of trials, and then we can figure out what the coefficients are in this case. So in this case, when we saw the concentration, when we doubled A, we doubled the rate, we saw 0, but we didn't have any experiment for B, so that would have to be our next experiment there. Now, just a word of our rate constant. It's only constant if the temperature and the activation energy also stay constant. Increasing the temperature actually increases the K, as would adding a catalyst. Now, when we look at this, the magnitude of K can actually indicate the speed of a reaction. A small constant would be a slow reaction, and a large constant would be a fast reaction. So again, if we go back to our expression here with A, when we're changing the concentration of A, that would be a pretty good rate of a reaction. But if K was something like this, then we'd actually see an increased rate of our reaction. So let's take an example here. Here we have three reactants creating some unknown products. And what we wanted to see is how each of these will have, or what effect the increasing the concentration of each of these would have on the overall rate of the reaction. So we've done our data collection and we tabulated it into this table over here. Now, to figure out all these different parts of it, what we're going to do is we're going to dissect this table a bit. But first, let's start off with what the rate law is using these variables. So our rate is going to be equal to some constant, we don't know what the constant is yet, multiplied by the initial concentrations of each of our reactants raised to some variable. So our concentration of A raised to some variable, in this case we'll just put M, multiplied by the concentration of B raised to some variable, multiplied by the concentration of C raised to some variable as well. I'm not going to put O because it looks too much like a 0. I'm going to put P. So there is a general expression for my rate law. Again, the rate is equal to some constant multiplied by the initial concentrations of each of the reactants raised to some kind of power. Now, what are the exponents for our rate law. So we have three exponents here. We have the exponent for A, we have exponent for the concentration of B, and we have the exponent for the concentration of C. Now what we have to do is we actually have to look at this table to figure out these exponents. So to figure out the exponent for A, I'm just going to put A, B, and C. We have to keep the other two reactants constant. So we have to look at this table over here. Now we see there's a change from 0.1 to 0.2, and we could actually use that to figure out our exponent, but we have to make sure that B and C are also constant, and we do. Here we see that these are constant while this one changes. So what we can do is we can relate this change in concentration to the change in the rate. So as we double the concentration of A, what do we actually see as a result in the rate? We see a doubling. So what this doubling means is that our exponent for M is going to be 1. It's going to be a linear relationship. So let's do the same thing for the other two. What we have to do is let's look at the concentration of B. Now when B is there, that means we have to keep A and C constant. So first of all, let's see whether we see a change. We can see a change from here, or from here. So we have to look at a scenario where both C and A are constant. So we'll take a look at this. Here we have from 0.2 and 0.2, so that's constant. 0.1 and 0.1, that's constant. And here we actually have a change in B. So let's look at the relationship here and see what that did to the rate. So again, because I'm looking at these two, trial 2 and trial 3, I'm also going to be looking at these two over here. Now what we've seen here is actually we've gone from 4.0 to 1.6 times 10 to the negative 3. So as we've doubled this concentration, we've seen a quadrupling of the actual rate. Now that would give us an exponent of 2. That's the only way we could do it mathematically. So that's going to be a second order reaction. Now for the last one, we have to look at the effect that changing the concentration of C has on the rate. We have to keep A and B constant. So here we see a change, 1 to 2, but this is not constant, that's not constant, so we can't use that. What about here? From this and here, we see that this is constant, but that's not constant, so that doesn't work either. How about from here? 0.1 to 0.2, that's a change. 0.1, 0.1, 0.1, 0.1. Okay, so we can look at C using our first and fourth experiments. So we've doubled up C, so let's see what happens to the rates, and we see no change. So what this means is that as we double up C, there's no change in the reaction, which means that it's going to be a zero order reaction. So going over here, let's see if we can figure out what the value of K is. Now we have to start off with our actual rate equation, so I'm just going to write that over here. Our rate is equal to K, A to the power of 1 because first order reaction, B to the power of 2, and C to the power of 0. Now because C is to the power of 0, it has no effect on the rate, we can actually drop it. So R is equal to K, A to the power of 1, and B to the power of 2. So in this case, we can just plug in our values. We can choose any one of these experiments. Experiment 1, 2, 3, 4, it doesn't really matter because they're all linked somehow. So I'm just going to choose experiment number 1. Okay. So to figure out what my K is, I know what my rate is. My rate is over here, and I know what my concentrations of A and B are. C, I also know the concentration of, but I dropped it because it's to the power of 0. So I know my variables here, I know my variable here, I can figure out K. So if I isolate for K, K will be equal to the rate divided by the concentration of A to the power of 1 times the concentration of B to the power of 2. So if I plug in my numbers, my number in this case is going to be 2.0 times 10 to the negative 4 mole per liter per second divided by the concentration of A, which is 0.1 times power of 1, and 0.1 times to the power of 2. So what we get here is we get a value of, for K, we get equal to 0.2. Now K does have a set of units. So what we have to look at is we have to look at the units that are included in our actual relationship here. So what I'm going to do is I'm going to do something a little bit different. I'm actually going to isolate the numbers from the units and help us see what's going on here. Now my units of R, in this case I'm going to use the same equation. I have K is equal to R over the concentration of A to the power of 1 to the concentration of B to the power of 2. So what I'm going to do is just use the units here. My R is actually mole per liter seconds, and that's divided by mole per liter, which is concentration of A, to the power of 1, times mole per liter to the power of 2. So if I do my calculation here, this is going to be mole squared times liter squared multiplied by mole and liter. So those multiplied means the exponents have to add. So I'll have mole per liter per second divided by mole cubed over liters cubed. Now here we have two dividing divisions, if you will. So what we can do is we can multiply by the reciprocal. So the multiplying of the reciprocal would be mole per liter times second multiplied by liters cubed over mole cubed. Now in this case, if we multiply this way, we can actually cross things out. My mole will cross out here, this will become a 2. My liter will cross out with the 3, and that will become a 2. So if I put this all together, what I'll get is I'll get liters squared over mole squared times second. And this is my unit for K. So it's going to be 0.2 liters squared divided by mole squared times second. That's my value for K. Now, it says here, the last one, it says express the rate law equation with the values obtained. So my rate is going to be equal to 0.2 liters squared mole squared per second multiplied to the concentration of A to the power of 1 and the concentration of B to the power of 2. Well, again, we can omit C because the power is a 0. So like we saw before, our units of our rate constant depend on the overall reaction order. Now we're going to get to this in a second, what the overall order is. If we go to the back one step, our rate was equal to K, A times power of 1 and B to the power of 2. So to figure out what the overall rate of the reaction is, all we do is we add the exponents. So 1 plus 2 gives us 3. And our third order reaction, well, look at that. Our third order overall, the units are liters squared per mole squared per times seconds, and that's exactly what we saw before. So if we know what the overall order is, we can also determine what the units of K are going to be. Now, please don't memorize these. Try to work them through like we just did in the previous example. That's the best way of learning this. So once again, the overall order of reaction, we can just add the sums of the exponents to give our overall order. And what this does is it helps us determine the mechanism at which these reactions take place. So most of the time, these reactions don't take place in a single step. They take place in a number of steps. And the step in that, the number of steps that is the slowest is actually going to be the one that determines the overall rate of the reaction. And so knowing what the overall order is will allow us to determine or give us an idea of what the mechanism or the number of series of steps are in this reaction. So thanks for watching. See you next time.